Welcome, my dear students. So, in the previous lecture, we have discussed about orthonormal sets and sequence in general, a special class of orthonormal set called total orthonormal set and their representation and their properties. So, from this lecture onwards, we will be try to represent linear functionals, especially bounded linear functionals, on a Hilbert space. So, our problem is to try to find a general form of an arbitrary linear functional or a bounded linear functional which is defined on a Hilbert space. In the case of a Banach space, this representation seems very difficult. But in the case of a Hilbert space, this representation becomes quite easy. In the case of a bounded linear operator, every bounded linear operator can be represented in terms of an inner product with regards to a single element. So that's the general idea which we obtain, which was proposed by Riesz, so which is called the famous Riesz's theorem. So let us quote the theorem. So this Riesz's theorem actually characterizes every bounded linear functional which is defined on a Hilbert space in terms of the inner product. So the result is every bounded linear functional f on a Hilbert space H can be represented in terms of the inner product, namely f of x is equal to inner product xz, where z depends upon f and is uniquely determined by f and has the norm z is equal to norm f. So, if you define an arbitrary linear functional on a Hilbert space, it always has the format f of x is equal to inner product xz. So, every bounded linear functional on a Hilbert space can be represented in terms of an inner product. And here, associated with f, there exists another element z. And the properties of z is unique with regards to f, meaning corresponding to every f there exists a unique z, or corresponding to every z there exists a unique f, and also both f and z has the same norm. So if you take an arbitrary bounded linear functional on a Hilbert space, it always has a representation in terms of an inner product with regards to some element. That element is unique with regards to the bounded linear functional, and also it has the same norm. So that's the general idea. So in using this result, you can actually characterize every bounded linear functional defined on a Hilbert space, because every bounded linear functional has a format inner product xz and depends upon a unique element z, and its norm can also be calculated using this result norm z is equal to norm f. So this is the general idea. So this is a Riesz's theorem of functionals on Hilbert space, linear functionals on a Hilbert space. So we need to prove this. The thing which we need to establish is, first we need to prove that f of x has the format inner product xz. Second, we need to establish that this z is unique. And third, we need to establish norm f is equal to norm z. So we need to prove that one, f of x is equal to inner product xz. Second, this z is unique. Third, norm f is equal to norm z. So these are the three things which we need to establish. So first, assume that f be a bounded linear functional on H. So let f be a bounded linear functional on H. Then we can divide f into two different cases. First case, if f is equal to 0. A 0 function is always a bounded linear functional, so f can be 0. So if f can be 0, then choose z is equal to 0. Then inner product xz is equal to inner product x0, which is equal to 0, which is equal to f. So f and inner product xz are actually same whenever f is equal to 0. And also norm f is equal to 0 since f is equal to 0. And when z is equal to 0, norm z is also 0. So which implies norm f is equal to norm z. So when f is equal to 0, you can choose z as 0 such that f of x can be written as inner product xz and norm f and norm z are actually same. So this is the first case. Next case, we will assume that f is actually non-zero. So consider that case 2, f is actually not equal to 0. So in that case, we choose our z to be non-zero, because if z was to be 0, then inner product xz was 0 whenever z is equal to 0. So which means that inner product xz should not be equal to f, because we assume that our f is actually non-zero. Okay. So now we will verify that. So now we will prove that f of x is equal to inner product xz. This is what we are going to prove. Now, as we consider, we have assumed that our z is actually not equal to 0. So we consider inner product xz to be 0. And this is for all x such that f of x is equal to 0, because we need it to be equal. So this implies f of x is equal to 0 means x element of the null space of f. Okay. So when x element of null space of x, we consider inner product xz is equal to 0. So which means that x and z are orthogonal. So x and z are orthogonal. So since x element of n of f, so which means z element of n of f perpendicular, the perpendicular space. Okay. Now we have already established that for a linear functional, n of f is always a vector space, actually a vector subspace, and it's a closed subspace. Refer theorem 2.6.9 and 2.7.10. In this theorem, we have established that the null space of a linear functional is always a vector space and it's a closed subspace. Then we can, by projection theorem, so by projection theorem, our Hilbert space can be written as nf direct sum nf perpendicular, where nf is a closed subspace. Projection theorem, according to projection theorem, we can write it in this form. Now since f is assumed to be non-zero, which means that there exists at least one x element of H such that f of x is actually non-zero. And this x, because every h is actually the direct sum of n of f and n of f perpendicular. So either if we choose an arbitrary element in h, either it should be an element in n of f or it should be an element in n of f perpendicular, or it has a format xy where x is element of n of f and y is an element of n of f perpendicular. That's this means. So since f is non-zero, there exists an x such that f of x not equal to 0. So which implies n of f is not completely h, because if n of f was h, then n of f perpendicular was set 0. Then which means that for all x element of h, f of x should have been equal to 0, because n of f perpendicular is equal to 0. Okay, so every element of h should be in the null space of f. Here, since f is non-zero, we can found at least one element of h such that f of x is non-zero. So which means that n of f cannot be equal to h, or there exists an z naught which is not equal to 0, which belongs to n of f perpendicular. Now using this z naught, we will find our z such that f of x is equal to inner product xz. So using this z naught, which is an element of n of f perpendicular, we define an arbitrary element v is equal to f of x times z naught minus f of z naught times x. So this is v for all x element of h, or x is an arbitrary element of h. Now f is a bounded linear function. We take f of v. So which means we substitute f of x times z naught minus f of z naught times x. So this should be equal to, f is a bounded linear functional. So we can take f of x times f of z naught minus f of z naught times f of x. So this is of the form a minus a, which should be equal to 0. So f of v is equal to 0 means v element of the null space nf. Since our choice of z naught, which is actually perpendicular to n of f, because we choose our z naught to be element of n of f perpendicular, z naught is actually orthogonal to every element of n of f. So z naught is actually orthogonal to v. So we can write 0 is equal to inner product v z naught, because by this assumption v is an element of n of f, z we have already chosen to be an element of n of f perpendicular. So since z naught and n of f are orthogonal, z naught is orthogonal to every element in n of f. So v is an arbitrary element of n of f, so v and z are actually orthogonal. Now we substitute the value of v. So v is actually f of x z naught minus f of z naught x comma z naught. So this can be written as inner product f of x z naught minus f of z naught x z naught. Now this should be equal to, we can take f of x outside, f of x times inner product z naught minus f of z0 times inner product x z0. Inner product z0 is norm z0 square. So f of x times norm z0 square minus f of z0 times inner product x z0. Since we have assumed our z0 to be non-zero, norm z0 is actually not equal to 0. So this should be equal to 0. So which implies we take this negative onto the other side. So we can rewrite f of x times norm z0 the whole square should be equal to f of z0 times inner product x z0, which implies in f of x should be equal to f z0 divided by norm z0 square times inner product x z0. We can write it this form. We can divide throughout by norm z0 square because norm z0 is actually non-zero. Now using the property of inner product, we can take this constant inside the second part, not the first component, in the second component. So this should be equal to x f of z0 by norm z0 square whole conjugate times z0, because from the second component if you take this outside, this should be conjugate times conjugate, which should be the element. So if you take this element onto the inside, we have to take the conjugate. Now we take this, that is f of z0 by norm z0 square the whole conjugate z0 as our z. So which implies f of x is of the form inner product xz. So f of x is also has the form inner product xz, where z is an arbitrary element of this form, which is obtained from z0, which is an arbitrary element of our choice, which is obtained from n of f perpendicular. So we have proved that f always has a format f of x is equal to inner product xz. So our first part is been completed. Now moving on to the second part. So we have chosen an arbitrary linear functional. Associated with that linear functional, we have found an z such that f of x is of the form inner product xz. Now moving on to the second part. In the second part, we have to prove that this z is actually unique. So second part, so we have to prove that z is unique. Okay. Now we take, let z1 and z2 be two elements such that f of x is equal to inner product xz1, which should be equal to inner product xz2. Okay. Now we have to prove that z1 and z2 are same. So this linear function is determined by z1 and as well as z2. We have to prove that z1 is equal to z2. So which implies inner product xz1 is equal to inner product xz2. So which implies inner product xz1 minus inner product xz2 is equal to 0, which implies inner product x z1 minus z2 is equal to 0. This is true for all x. So this is true for all x. So in particular, we choose x is equal to z1 minus z2 because this result is true for all x. Okay, so we can choose any x such that this result is true. So in particular I choose our x to be z1 minus z2. So which implies inner product z1 minus z2 comma z1 minus z2 is equal to 0, which implies norm of z1 minus z2 the whole square is equal to 0, which implies z1 minus z2 is equal to 0, which implies z1 is equal to z2. So we have proved that if f of x is equal to inner product x z1 is equal to inner product x z2, then z1 is equal to z2. So z1 and z2 are two elements which determines f, then z1 should be equal to z2. So every bounded linear functional is uniquely characterized by this z. So associated with every f bounded linear functional, we can choose a unique z such that f of x is equal to inner product x z. Now, third part, we have to prove that norm f is equal to norm z. Here also consider if f is equal to 0 and z is equal to 0, then which implies norm f is equal to 0 is equal to norm z. So when f and z are 0, this result is trivially being satisfied. Now consider the case when f is not equal to 0, then z is not equal to 0 because when z is equal to 0, inner product x z becomes 0. Here f is not equal to 0. And we can write f of x is of the form inner product x z, z is non-zero, x is an arbitrary element. Choose our x to be z. So f of z to be inner product z which should be equal to norm z the whole square. Or in other words, norm z the whole square should be equal to inner product z which should be equal to f of z, and since f is actually a bounded linear functional, modulus of this is actually less than or equal to norm f times norm z. Okay, we can take this modulus as well because we have considered norm z the whole square. Okay, and norm z the whole square is always positive. So that's the thing. Now, which implies norm z the whole square is actually less than or equal to norm f times norm z. Since z is not equal to 0, norm z is not equal to 0, so we can throughout divide with norm z, and which implies norm z is less than or equal to norm f. So this is equation number 1. Now secondly, modulus of f of x is actually equal to modulus of inner product x z. By Schwarz inequality, this should be equal to norm x times norm z by Schwarz inequality. You have to quote this. So which implies modulus of f of x is actually less than norm x times norm z. Now we taking the supremum over all x such that norm x is equal to 1. So supremum over modulus of f of x with norm x is equal to 1 should be less than or equal to, here norm x is equal to 1, this is norm z. Now this by definition is norm of f. So which implies norm of f should be less than not equal to norm Z. So this is equation number 2. So from 1 and 2, norm Z is less than or equal to norm F, and norm F is less than or equal to norm Z means norm F should be equal to norm Z. So we have proved all the sufficient parts to establish this result. Okay, so first we established that there exists an Z such that f of x is equal to inner product xz. Okay, that z is actually obtained from some z naught which belongs to n of f perpendicular, which is non-zero, and z has the format f of z naught divided by norm z naught square, the whole conjugate times z naught is actually z. Next we have proved that our choice of z is actually unique. Okay, third we have proved that norm f satisfies norm f is equal to norm z. And so which means that every bounded linear functional which is defined on a Hilbert space can be uniquely represented by an inner product with depends upon a unique element z. So this is the result. Thank you.